Let's look at some related rate problems. These are all going to be three pretty traditional problems that you find in most math classes. But this first one is the easiest one, and we're simply looking at, you throw a pebble into a lake or something and the ripples form. The ripples are getting bigger and bigger as time passes. And if you took just one of the ripples and you look at the circle that was being formed, the area is getting bigger and bigger. And this question is actually asking us for essentially the speed of area. How fast is the area changing? So it's kind of a different concept compared to what you've come across in like an algebra class or something. The way we start this is we just want to start with an expression for the area. So we know that area is pi r squared. Now, without much explanation, I'm going to take the derivative of this with respect to t. So I'm going to find d dt of really both sides of this equation. Not a very good math notation here, but you get the idea. So the derivative of a is going to be dA dt. And then pi is a constant, so it'll stay out on its own. And the derivative of r squared then is going to be 2r dr dt. So our implicit differentiation, right? We've got to multiply. Since the t and the a don't match and the t and the r don't match, I get a dA dt and a dr dt tagged on to the end of my derivatives. Well, if we think about this a little bit, we've got some information in this problem. Right here it says the outer ripple is increasing at a constant rate of 1 foot per second. Well, if you have a rate of anything, when you start seeing this word rate, it's always going to be d something dt. It's how fast something is changing with respect to time. In this case, our rate is of the radius. So that's going to give us dr dt. So when it says that the radius is changing at a constant rate of 1 foot per second, in terms of our math notation, that means that dr dt is 1 foot per second. By the same logic, if I was looking for the rate of the area, represented by an A, that's going to be dA dt. And that's what we're looking for in this problem. So as complicated as this looks, it actually turns out to be pretty simple because we have all the pieces. This is what I want. dA dt is what I'm looking for. And I actually know that dr dt is just 1. I also know that the radius is 4, which is given to me here, right? Radius is 4 feet. So if I plug all those pieces in, I'll have dA dt is equal to pi times 2 times the radius times the rate of change of the radius. And I'll get my answer to be 8 pi. Now before I put the units on there, let's think about these units for a second. I've got my dA dt is pi times the radius, which is actually 4 feet, right? And then times the rate, dr dt, which we have the units right here, is 1 foot per second. So if I multiply out these units, they come out to be square feet per second. Or you could think of this as area per time, which is exactly what we said at the very beginning of this problem, that what we're looking for is the speed of area. That would be how fast the area is changing with time. So with that in mind, we'll go back up and finish this problem. This 8 pi is in square feet per second. Another example, this time we've got a cone and the water's draining out, right? So this water level is decreasing. So I've got a height right here. This value is coming down further and further, which is going to make this radius shrink smaller and smaller as it goes, right? According to the information I have on here, I've got a 10-foot height on this and a 4-foot radius. As this is shrinking, we'll call that dr dt, is the rate at which that radius is getting smaller. And then coming down here, I've got, we'll say dh dt, is the rate at which the height is getting smaller. So in this problem, I've got that this dh dt is negative 0.3. That's feet per second, but I'm not going to mess up my drawing by throwing that in there. And then I've got dr dt is negative 0.1. And I'll just sort of keep all this information in mind as we solve this thing. First thing I need here is an expression for volume of a cone. And that's going to be 1/3 pi r squared h. Same idea as before. I want to take this derivative with respect to time. So derivative of v is going to be 1 times dv dt. Will give us dv dt here. And then I've got 1/3 pi, I'll kind of keep separate. And then in here, I have a product. Which means I'm using the product rule. So the product rule says that I will have r squared times the derivative of h, which is just dh dt, plus h times the derivative of r squared, which would be 2r dr dt. So hopefully that makes sense. Just, product rule applied to that thing. And at this point, this is where, this problem just looks so, complicated, and you got stuff everywhere. But if we stop and think about this, I know every one of these values now. They're all listed over here in this part. So I don't even really need to simplify anything. I can just start plugging in right now if I want. So if I did that, dv dt is going to be 1/3 pi still. And then inside our brackets, r squared is going to be 4 squared. dh dt is right here, is negative 0.3. And then I've got plus h, which we have over here, is 10. Times 2r, r is 4, so I can go ahead and plug that in. And then I've got dr dt right here, is negative 0.1. We get that dv dt is negative 13.4, this time cubic feet per second. Negative value is totally acceptable because the volume is actually decreasing, right, in this problem.